Picture this: you're floating in the endless void of space, surrounded by swirling galaxies, black holes that devour light, and planets where the laws of physics seem to rewrite themselves. It's a universe filled with mysteries that make even the brightest scientists pause and wonder, because here's the thing: space doesn't always play by the rules. In fact, there are moments when it outright defies them, leaving us scratching our heads in awe. And that's exactly what we're diving into today. 30 times the cosmos threw the rulebook out the window and left us staring into the abyss, questioning everything we thought we knew. Think about it. We grow up learning that nothing can travel faster than light, that gravity pulls everything downward, that energy can't just disappear. But what if I told you space laughs in the face of those rules? From stars that vanish without a trace to galaxies spinning faster than they should, the universe is packed with phenomena that shouldn't exist, and yet they do. It's like watching a magician perform tricks with no explanation, except this magician is the cosmos itself, and the secrets it's hiding are written in the fabric of reality. So why does this matter? Because every time space breaks its own rules, it's not just a cosmic glitch, it's a clue that maybe we don't have it all figured out yet. That there's so much more lurking out there, waiting to be discovered, and that's the real magic here, not just the mind-bending anomalies themselves, but what they reveal about our place in the universe. So buckle up, because we're about to take a journey through the most baffling, breathtaking moments where space said, "Forget the textbooks," and showed us just how little we truly understand. Get ready, this is going to change how you see the stars forever. One of the most head-scratching moments in space exploration history began with two tiny spacecraft hurtling toward the edge of our solar system. Pioneer 10 and Pioneer 11, launched in the early 1970s, were supposed to be humanity's first emissaries to the outer planets, but they carried back a mystery that would stump scientists for decades. As these probes journeyed farther from the sun, something bizarre happened. They started slowing down more than physics said they should. According to Newton's laws, their speed should have been predictable, governed by the sun's gravity alone. But the Pioneers were decelerating just enough to make scientists double-check their math, then triple-check it. At first, researchers assumed it was a glitch, maybe a thruster leak or a software error. But when the same unexplained drag showed up in both spacecraft, the implications became impossible to ignore. This wasn't a mistake, it was a signal. The universe seemed to be whispering that one of our most trusted equations, Einstein's general relativity, might be missing a piece. For years, theories ranged from the cautious to the wild. Maybe heat radiating unevenly from the probe's nuclear power sources was pushing them off course, like a teapot whistling steam in zero gravity. Or perhaps dark matter was tugging at them in ways we couldn't yet measure. But the most thrilling possibility, that gravity itself behaves differently over vast cosmic distances, rewriting the rules we thought were set in stone. What makes the Pioneer Anomaly so fascinating isn't just the unsolved puzzle, it's the humility it forced upon science. Here were two human-made objects, barely the size of a compact car, revealing that even our most fundamental assumptions about space might be incomplete. Decades later, most researchers leaned toward the thermal explanation, but the debate never fully closed, because in the end, the Pioneers did exactly what great explorers do. They ventured into the unknown and came back with questions we're still trying to answer. And that's the real lesson here. Sometimes the universe's greatest gifts aren't answers, but the mysteries that keep us reaching further. Galaxies should be flying apart. That's the startling truth astronomers faced when they first measured how fast stars were whirling around distant galactic centers. According to Newton's laws, the speed of those outer stars should drop off the farther they are from the galaxy's core, just like planets slowing down as they orbit farther from the sun. But when scientists crunched the numbers in the 1970s, they found something impossible. stars at the edges of galaxies were moving just as fast as those near the middle. It was as if the entire galaxy was glued together by some invisible force, some unseen hand gripping the stars and refusing to let them go. This wasn't a small miscalculation, it was a full-blown rebellion against physics. The visible matter in galaxies, stars, gas, dust simply didn't have enough gravity to explain those breakneck speeds. So either Newton's laws were wrong on cosmic scales, or there was something else out there, something we couldn't see. That's when the idea of dark matter took hold, a mysterious, invisible substance outweighing ordinary matter 5-1, its gravity weaving an unseen scaffold that holds galaxies together. Think of it like a cosmic puppet master pulling strings we can't see but can't ignore. The wildest part, we still don't know what dark matter actually is. It doesn't emit light, absorb it, or interact with ordinary matter in any way except gravity. It's like trying to study a shadow by the shape it leaves on a wall. Scientists have spent decades chasing clues, building detectors deep underground to catch stray particles, watching how dark matter bends light around galaxies, even smashing atoms together in colliders hoping to create it. And yet, it remains stubbornly out of reach. Some theories suggest it's made of exotic particles colder than the darkest depths of space. Others propose we've got gravity all wrong, and what we call dark matter is just the universe revealing a deeper law we haven't uncovered yet. What makes this cosmic tug-of-war so thrilling is how it humbles us. We've mapped the stars, landed on moons, even photographed the edge of a black hole, but most of the universe's matter is still a ghost to us. Every time we think we've pinned it down, it slips through our fingers like smoke, and that's the beauty of the mystery. Dark matter isn't just a puzzle to solve. It's a reminder that the cosmos is far stranger, far grander than our textbooks dared to dream. Einstein once called it his greatest blunder, a cosmic fudge factor he scribbled into his equations to keep the universe static, only to dismiss it later when the cosmos was proven to be expanding. But in a twist worthy of the grandest scientific irony, that very idea came roaring back to haunt us. Because in the late 1990s, astronomers made a discovery so shocking it ripped apart our understanding of cosmic destiny. The universe isn't just expanding, it's accelerating. And the force behind this runaway expansion, we still don't fully understand it, but we've given it a name that sounds like something from a sci-fi novel: dark energy. Picture throwing a ball into the air, expecting it to slow down and fall back to Earth, only to watch it shoot faster into the sky instead. That's the jaw-dropping reality astronomers faced when they measured distant supernova, the explosive deaths of stars used as cosmic mile markers. These stellar explosions were dimmer than they should have been, meaning they were farther away than expected. The only explanation, space itself was stretching faster over time, as if some invisible repulsive force was pressing its foot on the cosmic gas pedal. This wasn't just a minor adjustment to the rules, it was a full-throated rebellion against them. Einstein's discarded cosmological constant, once thought to be a mathematical hiccup, suddenly became the leading candidate for dark energy's identity, a kind of anti-gravity woven into the fabric of space itself. Think of it like a hidden spring in the vacuum of nothingness, relentlessly pushing galaxies apart. But here's where things get even weirder. Dark energy isn't just some minor player in the cosmic drama. It makes up nearly 70% of the universe's total energy budget, dwarfing everything else: stars, planets, even dark matter. And unlike gravity, which weakens with distance, dark energy's push grows stronger as the universe expands, creating a feedback loop that could one day tear atoms apart in what scientists call the Big Rip. What makes this cosmic plot twist so unsettling is how little we grasp about it. Is dark energy truly constant, or does it evolve over time? Could it someday vanish, reversing the universe's expansion into a catastrophic collapse? Or is this acceleration just the first act in a stranger story we haven't even imagined yet? Every telescope pointed at the night sky, every supernova analyzed, is another attempt to decode this puzzle, one that forces us to confront a humbling truth. The universe isn't just stranger than we suppose, it's stranger than we can suppose, and dark energy. It's the ultimate reminder that the cosmos still holds the pen when it comes to writing the rules. Imagine a flash of radio waves so powerful it outshines our entire sun, but only for a fraction of a second. No warning, no follow-up, just a brilliant cosmic scream vanishing as suddenly as it appeared. That's the enigma of fast radio bursts, or FRB, some of the most energetic and perplexing signals ever detected in the universe. First discovered in 2007, these fleeting pulses pack more energy than 500 million suns into mere milliseconds, arriving from galaxies billions of light-years away with no discernible pattern. It's like picking up a radio transmission where the station broadcasts one ear-splitting note, then goes silent for years. At first, astronomers wondered if these bursts were glitches, some earthly interference or equipment malfunction. But as more were captured by telescopes worldwide, the truth became undeniable. FRBs were real, and their origins were anything but ordinary, the leading suspect. Magnetars, the zombie stars of the cosmos. These ultra-dense remnants of dead stars possess magnetic fields so intense they could strip the data from a credit card halfway across the solar system. When one of these magnetars experiences a starquake, a violent crack in its rigid surface, the resulting energy release might just explain FRBs. Picture snapping a gigantic cosmic rubber band, sending a shockwave rippling through space at the speed of light. But here's where the mystery deepens. Some FRBs repeat. Unlike the one-off bursts, these recurring signals flash from the same patch of sky at irregular intervals, ruling out catastrophic events like collisions or explosions. Could it be alien technology? While most scientists consider that a last resort hypothesis, the sheer power and precision of FRBs have sparked serious debates. One particularly famous repeater, FRB 121811, seems to follow a rough 157-day cycle, almost like a lighthouse beam sweeping past Earth on a cosmic timetable. Whether it's natural or not, that kind of regularity suggests something far more structured than random stellar tantrums. The real puzzle lies in what FRBs reveal about the universe's hidden scaffolding. As these bursts travel across galaxies, they interact with the sparse particles floating between stars, leaving subtle fingerprints in their signals. This lets astronomers map the universe's missing matter, the diffuse gas and plasma too faint to see directly. It's like using lightning flashes to study the atmosphere. Each burst illuminates the invisible. What makes FRBs so thrilling isn't just their extreme physics or the remote chance they're messages from afar. It's the way they force us to rethink how energy behaves across cosmic distances. In a universe where magnetars can scream louder than entire galaxies and mysterious beacons flash without explanation, one thing's certain: space still holds the best surprises. And as our telescopes grow more sensitive, who knows what else might be listening in the static? In the quiet hours of August 15, 1977, a radio telescope in Ohio picked up a signal so extraordinary that the astronomer who discovered it scrawled, "Wow." In the margin of the printout, a burst of raw excitement that would give the phenomenon its name. Lasting 72 seconds, the wow signal came from the direction of the constellation Sagittarius, blasting at a frequency scientists had long theorized might be used for interstellar communication. It was 20 times stronger than the background noise of space, perfectly matched the expected signature of a non-natural transmission, and then vanished without a trace. Decades of searching have never found its like again, turning this fleeting cosmic whisper into one of astronomy's greatest unsolved riddles. What made the signal so electrifying was its precision. It hit exactly 1,420 MHz, a quiet frequency where hydrogen, the universe's most abundant element, barely emits noise. Scientists had once suggested this would be the ideal channel for aliens to broadcast on, a sort of universal hailing frequency. The signal also displayed a narrow bandwidth, a hallmark of engineered transmission rather than the messy scatter of natural cosmic events. Imagine tuning an analog radio and suddenly hearing a perfect, unwavering tone amid the static. That's how starkly the wow signal stood out from the cosmic background. Yet the very clarity that made it intriguing also deepened the mystery. If it was a deliberate broadcast, why hasn't it repeated? Was it a one-time beacon, a cosmic flare gun shot blindly into the dark? Or could it have been something more mundane, like a comet's hydrogen cloud reflecting sunlight? A hypothesis floated in 2016, though later disputed. The lack of answers has fueled speculation ranging from the sober to the sensational. Some argue it was a military satellite test, though no records match the event. Others whisper about a civilization briefly flicking their transmitter toward Earth before moving on. The most tantalizing possibility isn't just that we heard something, but that we might never know what. Unlike fast radio bursts or dark matter, the WOW signal left no residual clues, no afterglow to study. It's a single fingerprint on the universe's window, wiped clean before we could trace its source. And that's the haunting lesson it carries. Space might be full of messages we're not equipped to hear twice. Every night, telescopes still scan Sagittarius, listening for another whisper in the dark. Whether it's aliens, a quirk of physics, or something beyond our imagination, the WOW signal remains a humbling reminder that the cosmos loves a good mystery and isn't afraid to leave us guessing. Most stars flicker predictably like cosmic metronomes keeping time across the galaxy. But then there's KIC 8462852, better known as Tabby's star, a celestial rebel that doesn't just flicker. It plunges. Imagine watching a street lamp dim by 20% for days at a time, then brighten again. No warning, no pattern, just staggering dips in light that defy every textbook on stellar behavior. When astronomers first spotted this anomaly in data from NASA's Kepler telescope in 2015, the only thing clear was that nothing about it made sense. Initial theories swung from the mundane to the mind-bending. Could it be a swarm of comets blocking the star's light? Maybe, but the sheer scale required would dwarf our entire solar system's comet cloud. Dust clouds possibly, but why would they orbit so erratically? Then came the idea that set the internet ablaze: alien megastructures. Specifically, a Dyson swarm, a hypothetical civilization-built array of energy-harvesting satellites encircling the star. The notion wasn't entirely fringe. Even famed astrophysicist Jason Wright suggested it was worth considering. After all, Tabby's star's light patterns didn't match any known natural phenomenon. It was like finding a fingerprint where no hand should be, but science thrives on ruling out the extraordinary. Further studies revealed the dimming wasn't uniform across all light wavelengths, a telltale sign of something mundane like dust scattering shorter wavelengths more than longer ones. By 2018, new data confirmed micron-sized dust particles were the likely culprit, though their origin remains puzzling. Were they remnants of a shattered planet? Debris from colliding asteroids, the star itself sporadically coughing up opaque clouds. No one knows for sure. What's undeniable is how Tabby's star exposed the gaps in our understanding of stellar adolescence. Most stars its age, middle-aged F-type, should be stable, not throwing cosmic tantrums. The real legacy of Tabby's star isn't just the mystery it presented, but how it reshaped astronomy. It proved crowdsourcing could revolutionize science. Amateurs sifting through Kepler data flagged it years before professionals noticed. It forced researchers to consider wildly creative explanations without flinching. And most of all, it reminded us that the universe loves to subvert expectations. Whether it's dust or something we haven't even imagined yet, Tabby's star stands as a beacon of cosmic humility. A single strange flicker, and suddenly we're all beginners again. Even now, telescopes keep watch, waiting for its next dramatic dimming act. because in a universe where stars can vanish and reappear like stage magicians, the only certainty is this: the next big surprise is already written in the starlight. We just have to look up. Black holes aren't just cosmic vacuum cleaners, they're the ultimate enforcers of the universe's no-return policy. Once something crosses the event horizon, physics tells us it's gone for good, crushed into oblivion. But in the 1970s, Stephen Hawking dropped a bombshell that shook the foundations of physics. Black holes might not just swallow matter, they could be erasing the very fabric of reality itself. This wasn't just a quirky theory, it directly pitted Einstein's general relativity against quantum mechanics in a battle that's still raging today. Hawking's breakthrough was realizing black holes aren't entirely black. They emit a faint glow of particles, now called Hawking radiation, slowly leaking energy over billions of years until they evaporate entirely. But here's the catch: that radiation appears totally random, carrying no trace of the information about what fell in. That violates a sacred rule of quantum physics, the principle that information can never be truly destroyed. Imagine burning a book and being told the ashes hold no clues to its contents, then realizing even the smoke and heat are scrubbed clean of any memory of the words. According to quantum mechanics, that's impossible. The universe is supposed to be a meticulous librarian, keeping perfect records of every particle state. But black holes, they seem to be shredding the cosmic archives. This paradox set off decades of theoretical warfare. Some physicists argued the information must escape, hidden in subtle correlations within Hawking radiation. Others, like Hawking himself, initially bet it was lost forever. A stance so controversial it led to famous wagers with peers. The stakes, nothing less than whether the universe operates predictably at its core. If black holes really delete information, quantum mechanics would need a radical rewrite, and with it, our entire understanding of cause and effect. Enter soft hair. In 2016, Hawking and colleagues proposed a tantalizing solution. Perhaps information isn't destroyed but subtly imprinted on a black hole's event horizon via ultra-low energy particles, dubbed soft hair for their faint, wispy nature. Think of it like cosmic etch-a-sketch. When matter falls in, it leaves faint scratches at the boundary, preserving data in ways we're only beginning to decode. Recent breakthroughs in quantum gravity, like holographic principle research, suggest the horizon might act as a scrambled hard drive, with information preserved in its surface fluctuations, just in a form we can't yet interpret. Yet the debate is far from settled. Every proposed solution opens new questions. If information escapes, how? Does it leak slowly like a cosmic drips, or all at once in a final burst? Or is the paradox hinting at something deeper? A flaw in how we reconcile gravity with quantum theory. The sheer audacity of this puzzle is what makes it exhilarating. Black holes aren't just testing our knowledge, they're forcing us to invent new physics. And with telescopes now capturing images of event horizons, we might finally get the clues needed to crack the case. One thing's certain: whether through soft hair, holograms, or something even stranger, the universe hates losing information. The real mystery isn't just how black holes preserve it, but why they go to such theatrical lengths to make us think they don't. The moon shouldn't have a magnetic field. That's the puzzle scientists faced when Apollo astronauts brought back ancient lunar rocks in the 1970s, samples that bore the unmistakable fingerprints of a magnetic past. Here's what stumped them. Earth's magnetic shield comes from its churning molten core, a dynamo of swirling iron that generates our protective field. But the moon, it's too small, too cold, its core long since solidified. By all rights, it should be as magnetically dead as a pebble in space. Yet those Apollo rocks told a different story, one where the moon once held a magnetic field stronger than Earth's, lasting for over 1 billion years. It was like finding a fossilized light bulb in a cave. The evidence was undeniable, but the power source was missing. For decades, researchers wrestled with the paradox. How could a world with no molten core produce such a robust magnetic field? Early theories pointed to violent impacts, perhaps colossal asteroids striking the moon so hard they temporarily liquefied its interior, sparking a short-lived dynamo. But the math didn't add up. The field persisted far too long for such fleeting events. Then came a radical idea. Maybe the moon's mantle, not its core, was the engine. Computer simulations revealed that as the young moon cooled, its mantle may have convected in a way that churned residual heat like a slow-motion lava lamp, generating electrical currents capable of powering a magnetic field. Picture a pot of soup simmering just right, not boiling violently, but with enough movement to create subtle currents beneath the surface, but the plot thickens. Recent studies of lunar rocks suggest the field didn't fade smoothly. It flickered erratically, surging and waning in ways no current model fully explains. Some researchers now wonder if the moon's early orbit held the key. Billions of years ago, it sat much closer to Earth, and our planet's gravity may have stretched and squeezed its interior like cosmic Play-Doh, stirring up hidden reservoirs of heat. Others speculate that radioactive elements, concentrated in the moon's crust by ancient volcanic activity, acted like buried space heaters, prolonging the dynamo's life. What makes this mystery so tantalizing isn't just the moon's defiance of expectations, it's what it reveals about other worlds. If a small, rocky body like the moon could sustain a magnetic field without a molten core, could Mars have done the same in its youth? Might exoplanets we've written off as dead actually harbor hidden magnetic activity? Every new lunar sample, every refined simulation, peels back another layer of this enigma, and buried in those layers is a humbling truth. Sometimes the universe's greatest lessons come from the quietest places. The moon, our closest celestial neighbor, still guards secrets that could rewrite planetary science one magnetic whisper at a time. Somewhere beyond the Milky Way, hidden behind a thick curtain of stars and dust, an invisible force is rewriting the rules of cosmic motion. We call it the Great Attractor, a gravitational anomaly so powerful it's dragging entire galaxies, including our own, toward it at over 600 kilometers per second. The strangest part, we can't even see what's pulling us. This cosmic tug-of-war was discovered in the 1970s when astronomers noticed something odd. Hundreds of galaxies in our local supercluster were all streaming toward the same patch of sky near the constellations Centaurus and Hydra. According to the Big Bang's afterglow, the universe's expansion should send galaxies drifting apart like raisins in rising bread dough. But here they were, veering off course as if summoned by some unseen hand. The culprit lay 30 million light-years beyond the Milky Way's disk, buried in what astronomers call the zone of avoidance, a region so clogged with interstellar dust and bright stars that optical telescopes can't peer through it. It's like trying to spot a lighthouse through a blizzard. You know it's there by the light it bends, but the storm swallows the view. X-ray and radio telescopes eventually pierced the veil, revealing a density of galaxies so massive their collective gravity could explain the pull. But the shock came when scientists calculated the numbers. The Great Attractor's mass was far too small to account for the violent motion they observed. Something even bigger had to be lurking behind it. Enter Laniakea Hawaiian for immeasurable heaven, our home supercluster of 100,000 galaxies, with the Great Attractor acting as just a waypoint in a much larger flow. At its heart sits the Shapley supercluster, a behemoth 8 times more massive than the Great Attractor, yanking galaxies across 500 million light-years of space. What makes this gravitational mystery so thrilling isn't just the scale, it's the humility it demands. For centuries, we placed ourselves at the center of the cosmos, only to learn we're not even at the center of our own supercluster's dance. We're being pulled, along with everything around us, toward a destination we still don't fully understand. Every new map of galaxy motions peels back another layer, revealing a universe far more interconnected and far stranger than we ever imagined. The Great Attractor isn't just a place, it's a question written in gravity itself. What else is out there hiding in the dark? On October 19, 2017, astronomers spotted something streaking through our solar system that shattered every expectation. A mysterious visitor from interstellar space, tumbling end over end like a cosmic football. They named it Oumuamua, Hawaiian for scout, and at first glance it seemed like a routine space rock. But as telescopes tracked its path, something impossible emerged. This celestial drifter wasn't just coasting on gravity's pull. It was accelerating. The anomaly was subtle but undeniable. After slingshotting around the sun, Oumuamua should have gradually slowed as it raced toward the outer solar system. Instead, it gained speed, as if nudged by an invisible hand. Non-gravitational acceleration isn't unheard of. Comets do it when sunlight vaporizes their ices, creating jets that act like natural thrusters. But Oumuamua showed no visible coma or tail, no telltale puff of gas or dust. It was as if a car sped up without exhaust fumes, leaving scientists scrambling for explanations. The debate split the astronomy community. One camp argued for a stealthy outgassing scenario. Maybe Oumuamua was a comet after all, with its ices evaporating in ways too faint to detect. Hydrogen ice, for instance, could sublimate without leaving dusty traces, but would require an exotic composition never seen in local comets. Others proposed more radical ideas. Could radiation pressure from the sun, the gentle push of light itself, be responsible? For that to work, Oumuamua would need to be impossibly thin, like a solar sail crafted by nature. The most provocative hypothesis came from Harvard's Avi Loeb, who suggested it might be artificial, a relic of alien technology, perhaps a discarded light sail drifting between stars. Then there was the shape. Radar measurements suggested Oumuamua was elongated, perhaps 10 times longer than it was wide, unlike any asteroid or comet in our solar system. Add its unusual acceleration and lack of debris, and you had a trifecta of weirdness. Some researchers countered that our observations were simply too limited. Maybe it was a shard from a planet torn apart by its home star, or a fractal-like dust iceberg held together by cosmic forces we don't yet understand. The real frustration, we'll likely never know for sure. By the time Oumuamua's odd behavior was confirmed, it was already too far for follow-up observations, vanishing into the void like a ghost ship. Its legacy, though, is undeniable. It forced us to confront how little we understand about objects from beyond our stellar neighborhood. Was it a comet cloaked in mystery, a fragment of an alien world, or something even more extraordinary? The answer might be waiting in the next interstellar visitor, already on its way through the dark. Until then, Oumuamua remains the perfect cosmic riddle, a fleeting glimpse of the unknown, challenging us to think bigger. Quantum entanglement is the universe's ultimate magic trick, one where particles separated by light years somehow dance in perfect sync, defying every rule about how information should travel. Picture two coins flipped simultaneously on opposite sides of the galaxy, always landing heads and tails in perfect opposition, no matter how far apart they spin. This isn't science fiction, it's a phenomenon so bizarre even Einstein called it spooky action at a distance, convinced it revealed a flaw in quantum theory. But decades of experiments, including some conducted in the unforgiving vacuum of space, have proven entanglement isn't a flaw. It's the universe working exactly as designed, just not how we expected. The stakes couldn't be higher. According to relativity, nothing, not even information, can travel faster than light. Yet entangled particles mock this cosmic speed limit. Change the spin of one electron here on Earth, and its partner halfway across the Milky Way instantly mirrors that change, as if space and time between them don't exist. To test this mind-bending reality, scientists turn to space itself. In 2017, China's Misha satellite fired pairs of entangled photons to ground stations over 1,200 kilometers apart, shattering previous distance records for entanglement tests. The result, the particles stayed perfectly correlated, their connection unbroken by the vastness between them. It's like whispering a secret in New York and having your friend in Tokyo finish your sentence without missing a beat. But here's where it gets even weirder. This instantaneous link doesn't transmit usable information. No messages, no signals, just an unbreakable bond that seems woven into the fabric of reality. Some theorists suggest entanglement hints at a deeper layer of existence, where separation itself is an illusion and every particle in the universe is subtly connected. Others propose it's evidence of extra dimensions, with particles communicating through hidden folds in space-time we can't perceive. Then there's the radical idea that entanglement doesn't involve any transfer at all, that the particles were never truly separate to begin with, their fates locked together like two sides of the same cosmic coin. What makes these space-based experiments so groundbreaking is how they eliminate earthly interference. On Earth, air molecules and stray photons can disrupt delicate quantum states. But in orbit, scientists can test entanglement across distances impossible on the ground, pushing the boundaries of what we know. Recent missions even aim to use the International Space Station as a quantum lab, probing whether gravity itself affects entanglement, a question that could bridge quantum mechanics and general relativity. The implications are staggering. If entanglement holds across galactic scales, it might revolutionize secure communication with unhackable quantum networks spanning planets. Or it could reveal that the universe is far more interconnected than we dreamed, with every star, every atom subtly in sync. One thing's certain, every time we test entanglement, space reminds us its rulebook was written in invisible ink. And we're just starting to decipher the words. The universe is unimaginably vast, hundreds of billions of galaxies, each with billions of stars, many hosting planets in the so-called Goldilocks zone where life could thrive. With numbers like these, the math seems undeniable. The cosmos should be teeming with civilizations. So where is everybody? This is the crushing weight of the Fermi paradox, the staggering disconnect between our expectations of alien life and the eerie silence that greets us when we listen. In the 1950s, physicist Enrico Fermi posed the question bluntly during a lunchtime conversation at Los Alamos. If intelligent life is common, why haven't we found any evidence of it? The Drake equation, developed a decade later, tried to quantify the odds, estimating variables like star formation rates, habitable planets, and the likelihood of intelligence emerging. Plug in optimistic numbers, and the equation suggests there should be thousands, even millions, of technological civilizations in our galaxy alone. Yet our radio telescopes hear nothing but static. No signals, no megastructures, no cosmic engineering projects, just silence. One chilling explanation is the Great Filter, a hypothetical barrier that prevents life from advancing to interstellar scales. Maybe the filter is behind us, a fluke that let Earth dodge cosmic extinction events. But if it's ahead of us, lurking in our future, that implies every advanced civilization hits a wall, whether through self-destruction, AI catastrophes, or some unseen cosmic threat we haven't encountered yet. It's like walking through an empty city and finding only skeletons at their desks. The silence isn't just puzzling, it's a warning. Others argue we're simply too primitive to recognize alien activity. Could advanced civilizations communicate in ways beyond our comprehension using neutrino beams, quantum entanglement, or space-time ripples we can't yet detect? Or perhaps they've transcended physical forms, uploading themselves into digital realms invisible to our telescopes. Then there's the zoo hypothesis, the idea that Earth is deliberately left undisturbed, a cosmic wildlife preserve where younger species evolve without interference. But the darkest possibility, that we truly are alone, that in all this immensity, life is so unfathomably rare, Earth might be the only spark in the dark. Whether the answer is cautionary, hopeful, or humbling, the Fermi paradox forces us to confront a profound truth. The universe doesn't owe us answers. And in that silence, we're left to wonder, are we the exception or just the first to ask the question? Cosmic microwave background radiation should be the ultimate snapshot of randomness, a relic of the Big Bang's afterglow, stretching across the universe in a near-perfect mosaic of hot and cold spots. But in 2004, scientists staring into this primordial light stumbled onto something that shouldn't exist. A bizarre alignment nicknamed the axis of evil, where the CMB's fluctuations mysteriously correlate with the plane of our solar system. It's as if the universe left a fingerprint pointing directly at us, violating one of cosmology's sacred principles, the idea that no place in space should be special. The discovery sent shockwaves through physics. According to the standard model, the CMB should look statistically identical in all directions, a relic of quantum fluctuations magnified by the Big Bang's expansion. But when researchers analyzed data from NASA WMAP satellite, they found that larger-scale temperature variations weren't distributed randomly. Instead, they seemed to align along an axis that bizarrely matched the ecliptic, the plane where Earth and other planets orbit the Sun. The odds of this happening by chance, less than 1 in 1,000. It's like rolling a pair of dice 100 times and getting snake eyes every single time. Either the universe is playing a cosmic joke or we're missing something fundamental. Some theorists argue it's a fluke, an artifact of measurement errors or incomplete data. But subsequent observations, including those from the Planck satellite, only deepened the mystery. The alignment persisted, and stranger still, it wasn't just the ecliptic. The CMB's quadrupole and octopole moments, fancy terms for its larger scale patterns, also showed unexpected correlations with Earth's motion through space. This isn't just a coincidence, it's as if the fabric of reality itself has a subtle warp, one that somehow remembers our solar system's orientation. The most radical explanations venture into uncharted territory. Could the axis of evil be a relic of something before the Big Bang? Some models of loop quantum gravity suggest our universe might be the offspring of a collapsing predecessor, inheriting faint imprints of its structure like cosmic DNA. Others propose we're seeing evidence of a multiverse, where neighboring universes exert gravitational tugs on ours, leaving faint brushstrokes in the CMB. Then there's the mind-bending idea that we're observing quantum entanglement on a cosmological scale, where particles separated at the birth of the universe remained mysteriously linked across billions of light years. But perhaps the most humbling possibility is that we're simply not interpreting the data correctly. The CMB is the oldest light we can see, and decoding its secrets requires peeling back layers of interference from galaxies, dust, and even our own Milky Way's magnetic field. What looks like an axis might be a quirk of how we're mapping the universe, like mistaking a smudge on a telescope lens for a distant galaxy. What makes the axis of evil so tantalizing isn't just the anomaly itself, it's the questions it forces us to confront. Is the universe truly isotropic, or are we living in a cosmic funhouse where the rules change depending on where you stand? Every new observation, every refined model, brings us closer to an answer that could rewrite cosmology's foundational tenets. Until then, the axis of evil remains a ghost in the machine, a whisper from the universe that maybe, just maybe, we're not as insignificant as we thought. Neutron stars are the universe's ultimate timekeepers, spinning with such precise regularity that their pulses rival atomic clocks. But every now and then, one of these cosmic metronomes hiccups, lurching forward in a split-second speedup that shouldn't be possible. Astronomers call these events glitches, and they're among the most baffling behaviors ever observed in celestial objects. Imagine a figure skater pulling their arms in to spin faster, except in this case, the skater is a city-sized ball of nuclear matter weighing more than our sun, and no one touched it. The physics behind neutron stars reads like something from a sci-fi novel. Born from the collapsed cores of supernova explosions, these stellar corpses pack so much mass into such a small space that a teaspoon of their material would weigh 1 billion tons on Earth. Their crusts are thought to be a crystalline lattice of iron nuclei, while the interiors are a quantum soup of free-flowing neutrons and exotic particles. Most of the time, their rotation slows gradually as they bleed energy into magnetic fields and radiation. But during a glitch, the star suddenly spins faster, as if an invisible hand gave it a push. What could possibly cause such a violation of fluid dynamics? The leading theory involves a phenomenon called vortex unpinning. Picture the star's superfluid core, a frictionless quantum liquid where neutrons move in perfect unison. Normally, these vortices are anchored to the crust, keeping rotation in lockstep. But if the crust weakens under immense strain, those vortices can break free, transferring angular momentum to the surface in a sudden burst. It's like uncorking a bottle of champagne. The built-up energy releases all at once, giving the star a fleeting speed boost. Yet not all glitches fit this tidy explanation. Some neutron stars exhibit anti-glitches, where they mysteriously slow down instead. Others, like the famous Vela pulsar, glitch in near-perfect cycles as if on a cosmic schedule. Then there's the 2019 case of Magnata 183000486, which didn't just glitch. It emitted a series of bizarre radio bursts during the event, suggesting a turbulent interplay between its crust and magnetic field. These outliers hint at forces we don't yet understand, possibly involving exotic states of matter or even cracks in the star's ultra-dense surface. The stakes go beyond astrophysics curiosity. Neutron star glitches are natural laboratories for studying matter under conditions impossible to replicate on Earth, pressures so extreme they might stabilize rare particles like strange quarks. Some theories suggest these speedups could even generate ripples in spacetime itself, detectable by next-generation gravitational wave observatories. What makes these cosmic hiccups so thrilling isn't just their defiance of expectations, it's the humility they force upon us. After decades of observation, we still can't predict when or why a glitch will occur. Every time one happens, it's as if the universe is reminding us, even the densest, most well-mapped objects in the cosmos still hold secrets, and in those fleeting moments of chaos, we catch a glimpse of physics pushed to its breaking point. Measuring the universe sounds straightforward, like tracking how fast a balloon inflates. But when cosmologists actually try, they hit a snag so puzzling it's been dubbed the Hubble tension. Here's the problem: depending on how you measure it, the universe's expansion rate gives wildly different answers, and the gap between them keeps growing. It's as if two perfectly tuned clocks started ticking out of sync, and no one can figure out why. The first method relies on the cosmic microwave background, the afterglow of the Big Bang. By analyzing tiny temperature fluctuations in this ancient light, scientists can calculate how fast the universe should be expanding today. But when they check that number against observations of nearby stars and supernova celestial yardsticks called standard candles, the real-time measurements come up significantly faster. We're talking about a difference of roughly 7 kilometers per second per megaparsec, which might sound trivial until you realize it implies the universe is expanding almost 10% faster than our best models predict. That's not a rounding error, it's a crack in cosmology's foundation. One camp argues the discrepancy stems from overlooked quirks in our measurements. Maybe supernova aren't as uniform as we assumed, or interstellar dust is subtly dimming their light. But as observations sharpen, these explanations crumble. The other possibility: our understanding of cosmic ingredients is incomplete. The standard model assumes dark energy is a constant force, Einstein's cosmological constant. But what if it's been slowly strengthening over billions of years? Or perhaps dark matter interacts with itself in ways we haven't accounted for, subtly altering the universe's growth rate. Then there's the nuclear option. Maybe we need entirely new physics. Some theorists propose early, dark radiation briefly turbocharge the young universe, while others speculate about extra dimensions warping spacetime in ways we can't detect. The most radical idea: our universe collided with a neighboring bubble of reality in its infancy, leaving permanent wrinkles in the expansion rate. What makes the Hubble tension so thrilling isn't just the mystery, it's the stakes. If the discrepancy holds, it could force a rewrite of everything from particle physics to gravity itself. Every new telescope, from JWST to upcoming gravitational wave detectors, is now hunting clues. Because in this cosmic tug-of-war between prediction and observation, one thing's clear: the universe is hiding something big, and the longer the tension lingers, the more it feels like we're on the brink of a revolution. The only question is how deep the rabbit hole goes. Physics textbooks have a sacred rule: for every action, there's an equal and opposite reaction. Rocket engines push exhaust backward to thrust forward. Solar sails bounce photons for momentum. But in the late 90s, a British engineer named Roger Scheuer proposed something that should have been laughable: an engine that creates thrust without expelling anything. No fuel, no exhaust, just push. The M drive, as it came to be called, wasn't just breaking Newton's laws, it was setting them on fire. And yet, when NASA Eagleworks lab tested it in 2014, their instruments registered a whisper of force where none should exist. The scientific world collectively gasped. Had we stumbled onto warp drive's first cousin, or was the universe just messing with us? The M drive's design reads like science fiction. Picture a truncated copper cone like a rocket nozzle, sealed at both ends, pumped full of microwaves bouncing chaotically inside. According to Scheuer's controversial theory, these microwaves would exert more pressure on the cone's wider end, creating net thrust without any propellant. It's the equivalent of sitting in a car and pushing on the dashboard to make the whole vehicle move forward. By conventional physics, that's not just impossible, it's nonsensical. Momentum must be conserved. You can't get motion from nothing. Yet in vacuum chamber tests, the M drive reportedly produced micronewtons of thrust. Not much, but enough to raise eyebrows. Skeptics pounced immediately. Maybe the thrust was an artifact of thermal expansion, the copper heating unevenly and warping minutely. Or perhaps Earth's magnetic field interacted with power cables in the lab, creating false signals. The most damning critique: peer-reviewed studies failing to replicate the effect under controlled conditions. Yet the intrigue persisted because of where the anomalies appeared. Not just fringe labs, but NASA and China's space agency both reported fleeting successes. Even Germany's Dresden University, in a painstaking 2021 experiment, measured thrust only to later trace it to external magnetic interference. The M drive became a hall of mirrors. Every positive result had an explanation, but the explanations never quite killed the dream. What makes this saga so compelling isn't just the defiance of physics, it's what it exposes about how science grapples with the impossible. For years, researchers tiptoed around the M drive, afraid of professional ridicule yet unable to ignore the tantalizing "what if?" Some theorists scrambled to explain it within known physics, suggesting the device might somehow interact with quantum vacuum fluctuations, a sea of virtual particles popping in and out of existence. Others, like Scheuer himself, proposed radical revisions to momentum conservation. Meanwhile, aerospace engineers whispered about the implications. A thruster that didn't need fuel could revolutionize space travel, cutting Mars mission times from months to weeks. In the end, the M drive likely joins the ranks of cold fusion and N-rays, a cautionary tale of measurement errors and wishful thinking, but its legacy lingers in the questions it forced us to ask. How do we balance open-mindedness with skepticism? When does impossible become not yet? And most hauntingly, what if just once the outlier wasn't a mistake? The universe has surprised us before. Maybe one day it'll do it again. Beyond the orbit of Neptune, where sunlight is 1,000 times dimmer than on Earth, lies a cosmic frontier that shouldn't end but does. The Kuiper Belt, a sprawling disk of icy debris left over from the solar system's birth, stretches for billions of miles, filled with dwarf planets, comets, and frozen relics of planetary formation. Yet around 50 astronomical units from the Sun, about 7.5 billion kilometers out, something bizarre happens. The belt's population of objects doesn't gradually thin out as you'd expect. It plummets, dropping off like a cliff's edge into nothingness. Astronomers call this boundary the Kuiper Cliff, and its existence is one of the solar system's most tantalizing puzzles. This isn't just a case of our telescopes missing faint objects. Deep surveys like those conducted by the Subaru telescope and the Dark Energy camera have scoured these distant reaches with enough sensitivity to spot icy bodies far smaller than Pluto. Yet beyond the cliff, the detections nearly vanish. It's as if someone drew a line in the cosmic sand and said, "No further," the most obvious explanation. A hidden planet massive enough to have cleared a path through the belt with its gravity. This hypothetical world, often dubbed Planet 9, would need to be several times Earth's mass, lurking hundreds of astronomical units away in a slow, looping orbit. Its gravitational pull could shepherd Kuiper belt objects into peculiar clustered orbits, while leaving the region beyond the cliff suspiciously empty. But alternative theories abound. Perhaps the cliff marks the outer edge of the primordial disk from which our solar system formed, a fossilized boundary from a time when the Sun's birth cluster of stars stripped away material beyond this point. Or maybe a rogue star passed uncomfortably close billions of years ago, stealing the outer Kuiper belt's objects in a gravitational heist. There's even a wilder possibility that our solar system once had a fifth giant planet, an ice giant like Uranus or Neptune, that was violently ejected in the early chaos, scattering the belt's outer reaches as it fled. What makes this mystery so gripping isn't just the missing objects, it's what their absence reveals about the solar system's turbulent youth. The Kuiper belt is a time capsule, preserving clues about the gravitational tugs, collisions, and migrations that shaped the planets. Every odd orbit, every gap and cluster is a breadcrumb trail leading back to those primordial storms, and the cliff, it's either a signpost pointing to a world we've yet to discover or a scar from a cataclysm we're only beginning to understand. For now, all we have are questions, but with next-generation telescopes like the Vera Rubin Observatory coming online, the hunt for answers is heating up. Will we find Planet 9 lurking in the dark, or will the cliff remain a silent witness to forces we've yet to imagine? Either way, one thing's certain: the edge of our cosmic backyard holds secrets far stranger than we've dared to guess. We've mapped galaxies, weighed black holes, even calculated the universe's total matter down to a few percentage points. But here's something that kept cosmologists up at night for decades: half the universe's normal matter, the stuff that makes up stars, planets, and us, was simply missing. Not dark matter, not some exotic particle, but ordinary protons and neutrons that should have been easy to spot. Astronomers called it the missing baryon problem, and it was like misplacing an entire ocean while somehow keeping track of every drop. The numbers were undeniable. When scientists tallied up all the visible matter, every galaxy, every gas cloud, every speck of cosmic dust, it accounted for less than half of what the Big Bang's afterglow said should exist. According to the cosmic microwave background, baryonic matter makes up roughly 5% of the universe's total energy budget, yet our telescopes could only find about half that amount. Where was the rest, hidden in plain sight? It turns out woven into the universe's very scaffolding. The breakthrough came when astronomers realized they'd been looking for needles in all the wrong haystacks. Instead of searching for bright, concentrated objects like stars, they turned their attention to the faint, diffuse threads connecting galaxies, the cosmic web. These filaments, stretching millions of light years across the void, are made of superheated gas so sparse it's practically invisible. We're talking about plasma with temperatures upwards of 10 million degrees, so energetic it emits X-rays rather than visible light. Catching this faint glow required telescopes like ESA's XMM Newton and NASA Chandra, tuned to see the universe in high-energy wavelengths, and there it was, the missing matter hiding in these vast intergalactic rivers. Not in galaxies, not in black holes, but in the delicate lacework between them. The numbers finally added up. These filaments contain enough baryons to solve the mystery, their combined mass dwarfing every star and planet in existence. It's like realizing the air in a room weighs more than the furniture. You just needed the right scale to measure it, but the story doesn't end there. Why did this gas remain so elusive for so long? Part of the answer lies in its temperature and density. Hotter gas emits weaker spectral lines, making it nearly transparent to optical telescopes. And because these filaments are so thinly spread, averaging just a few atoms per cubic meter, they barely interact with light passing through them. Even now, mapping their full extent is like trying to trace a spiderweb with a flashlight in a hurricane. The missing baryon problem isn't just a census exercise, it's a window into how the universe structures itself. These filaments aren't passive leftovers, they're dynamic highways funneling gas into galaxies and fueling star formation. Some researchers believe they also play a role in accelerating cosmic rays to near light speeds. And because this gas is so ancient, barely altered since the Big Bang, studying its composition could reveal secrets about the universe's earliest moments. What makes this discovery so profound isn't just that we found the missing matter. It's how it reshaped our understanding of cosmic geography. Galaxies aren't isolated islands, they're knots in a grand tapestry, connected by rivers of fire too faint to see but too vast to ignore. And somewhere in those glowing threads lies the answer to another question. If we overlooked something this fundamental for so long, what else is waiting to be found? The universe has a speed limit not just for light but for cosmic rays too. And according to every known law of physics, ultra-high-energy cosmic rays coming from distant galaxies should have hit a wall long before reaching Earth. Yet here they are, crashing into our atmosphere with energies so absurd they make particle colliders look like toys. This is the Greisen-Zatseping-Kuzmin paradox, or GZK paradox for short, and it's one of the most stubborn puzzles in astrophysics. At the heart of the mystery is something called the cosmic microwave background, the faint afterglow of the Big Bang that permeates all of space. For ultra-high-energy protons traveling across intergalactic distances, this background radiation isn't just static, it's an obstacle course. Every time one of these protons collides with a microwave photon, it loses energy like a marathon runner tripping over hurdles. The math is clear. Any proton with energies above a certain threshold, what scientists call the GZK cut-off, should be drained of its power long before it reaches us. The universe, it seems, has a built-in speed bump for cosmic rays, but nature loves breaking its own rules. In the late 1990s, observatories like the Pierre Auger Array started detecting cosmic rays with energies far beyond the GZK limit, some carrying the kinetic equivalent of a fast-pitched baseball in a single subatomic particle. Even stranger, these rays appeared to originate from galaxies hundreds of millions of light-years away distances, so vast they should have made the particle's journey impossible. It's as if someone fired a bullet through a brick wall, only for it to emerge unscathed on the other side. So how are these cosmic rays cheating the system? One possibility is that our understanding of particle physics is incomplete. Maybe protons at these extreme energies interact with the cosmic microwave background in ways we haven't yet imagined, perhaps bouncing off it like a stone skipping across water instead of plowing straight through. Others suggest these ultra-high-energy particles aren't protons at all, but heavier nuclei like iron, which might be more resilient on their marathon trek through intergalactic space. Then there's the wildcard theory. What if these cosmic rays aren't coming from as far away as we think? Some researchers speculate they could be the fingerprints of near, by yet undiscovered phenomenon cosmic accelerators lurking in our galactic backyard. Magnetars, for instance, could theoretically rev up particles to these insane energies, though we've yet to catch one in the act. But the most tantalizing idea is that the GZK paradox is pointing us toward new physics altogether. Could there be exotic particles beyond the standard model zipping through space, unaffected by the usual energy loss mechanisms? Or are we seeing hints that spacetime itself behaves differently at these extreme scales, offering hidden shortcuts for high-energy travelers? What makes this cosmic conundrum so thrilling isn't just the particles themselves, it's what they reveal about the universe's hidden rulebook. Every time one of these ultra-high-energy rays slams into Earth's atmosphere, it's not just a scientific anomaly. It's a challenge, a dare from the cosmos to look deeper, question harder, and embrace the possibility that even the most well-tested laws might have cracks we've yet to discover. And in those cracks, that's where the real magic happens. The Boötes void shouldn't exist. Imagine a sphere of space so vast you could fit 2,000 Milky Ways side by side across it, then strip out nearly all the galaxies, leaving behind a cosmic desert spanning 330 million light-years. That's the Boötes void, a gaping hole in the universe's large-scale structure so empty it defies everything we know about how matter clusters. If the cosmos is a web of galaxies strung along glittering filaments, this is the place where the threads snap, leaving a void so profound it feels less like a gap and more like a deliberate erasure. When astronomers first mapped this region in the 1980s, they assumed their instruments were faulty. The universe, after all, isn't supposed to have voids this large. According to the standard model of cosmology, matter should be distributed relatively evenly across vast distances, with galaxies gravitationally drawn into clusters, walls, and filaments. The Boötes void, though, is a staggering outlier. While most cosmic voids average around 100 million light-years wide, this one dwarfs them all, with fewer than 60 galaxies scattered across its expanse, a number so low you could fit them all into a corner of the local group and hardly notice. It's like walking into a city expecting crowds and finding a single lamppost in an empty field. So how did this nothingness come to be? One theory suggests it's the ghostly imprint of an ancient collision between smaller voids, merging like soap bubbles to create a vacuum on a scale we've never seen. Another idea posits that dark energy, the mysterious force accelerating the universe's expansion, might have stretched this region thin earlier than most, leaving galaxies isolated and starved of neighbors. But the most unsettling possibility that the void isn't empty at all. It could be packed with dark matter, invisible and unknown, warping the space around it into a gravitational mirage that makes the region appear emptier than it is. What makes the Boötes void so unnerving isn't just its size, it's the questions it forces us to confront. Could there be other voids this large lurking in the unseen reaches of the cosmos? Are we staring into a flaw in the universe's blueprint? Or is this the signature of something deeper, something we haven't even begun to grasp? Every time we point a telescope at this abyss, it whispers back the same unsettling truth. The universe holds voids so vast they make emptiness feel alive. Mars should be a dead world, a frozen desert where chemistry plods along at a glacial pace. But in 2013, NASA, a Curiosity rover, sniffed something in the thin Martian air that sent shockwaves through the scientific community: methane. Not just trace amounts either. Spikes of the gas flared up unpredictably, sometimes reaching concentrations 10 times higher than background levels before vanishing without a trace. The discovery was explosive not because methane is rare in the universe, but because on Earth 95% of it comes from living organisms. Had Curiosity just stumbled onto the first whisper of alien life, the mystery only deepened with time. Methane on Mars shouldn't linger. Sunlight and chemical reactions should break it apart within a few hundred years. Yet Curiosity's readings showed fleeting surges, implying an active source replenishing it somehow. Even stranger, the European Space Agency's Trace gas orbiter, circling Mars since 2016, repeatedly failed to detect methane in the global atmosphere, even during Curiosity's spikes. It was as if the rover had parked over a hidden geyser belching gas that vanished before satellites could spot it from orbit. Possible explanations split into two fraught camps, geology or biology. On Earth, microbes called methanogens thrive in places devoid of oxygen, swamps, volcanic vents, even animal guts, churning out methane as a byproduct. Could similar organisms be lurking beneath Mars' icy soil, shielded from radiation? The idea isn't far-fetched. Subsurface aquifers or hydrothermal systems might offer just enough shelter and energy for microbial life to cling on, releasing gas through cracks in the surface. But the geological alternatives are just as tantalizing. Methane can form when water reacts with certain minerals like olivine in a process called serpentinization. Or it might seep from ancient methane clathrates ice-like deposits trapping the gas underground since Mars' wetter past. Some researchers even suggest meteorites could deliver organic material that sunlight then converts to methane. The problem: none of these processes easily explain the sudden bursts Curiosity observed. Geology tends to be slow and steady, not erratic like a blinking signal. Then there's the detective work of tracing the methane's origin. In 2019, scientists noticed a curious pattern. The spikes often occurred during Mars' northern summer, hinting at seasonal release. Could temperature changes be cracking open frozen reservoirs or stimulating hidden microbial colonies? Curiosity also caught whiffs of other organic molecules like benzene and propane woven into the methane spikes, complicating the puzzle further. These heavier compounds are more likely to form through geological than biological processes, muddying the waters. The stakes couldn't be higher. If the methane is biological, it rewrites our understanding of life's tenacity. If it's geological, it reveals dynamic processes still reshaping Mars today, processes that might create habitable niches for future explorers. NASA's Perseverance rover, equipped with sharper tools, is now hunting for answers, while ESA's upcoming Mars sample return mission might finally settle the debate. For now, the methane remains a riddle wrapped in a gust of Martian wind. Whether it's the breath of microbes or the sigh of ancient rocks, one thing's certain: the red planet is far from dead. It's a world of whispers, teasing us with clues we're only beginning to decode. And every time Curiosity's instruments twitch, we're reminded Mars still has stories to tell. Venus was supposed to be a cautionary tale, a hellish world where runaway greenhouse effects baked away any hope of life, leaving behind clouds of sulfuric acid and crushing pressures. But in September 2020, astronomers dropped a bombshell that turned planetary science on its head. They detected phosphine gas in Venus' upper atmosphere. Why does that matter? Because on Earth, phosphine is almost exclusively produced by living organisms, anaerobic microbes, thriving in oxygen-free environments like swamps and animal guts. Finding it on Venus was like smelling a distant barbecue on the wind in the middle of a lifeless desert. The discovery, made using the James Clerk Maxwell Telescope in Hawaii and later backed by the Atacama Large Millimeter Array in Chile, sent ripples through the scientific community. The phosphine signatures appeared at about 50 kilometers above Venus' surface, a sweet spot where temperatures and pressures are eerily Earth-like, floating in a haze of water vapor and sulfuric acid droplets. It was the closest thing to a neon sign for alien life we'd ever seen. The team, led by astronomer Jane Greaves, took pains to rule out non-biological explanations, from volcanic activity to meteorite delivery. Their conclusion: either Venus harbored some exotic, unknown chemistry, or we were staring at the first credible hint of life beyond Earth. But science thrives on skepticism. Within weeks, other researchers began poking holes in the findings. Some argued the phosphine signal could be a false positive, a misidentification of sulfur dioxide, a gas Venus' atmosphere is already packed with. Others pointed out that non-biological processes like lightning or bizarre atmospheric reactions might produce phosphine under Venus' unique conditions. The debate grew so heated that NASA and ESA fast-tracked new missions to Venus, desperate to settle the question. By 2021, the pendulum had swung hard. Independent teams reprocessing the original data found weaker or outright absent phosphine signals. One study suggested the initial detection might have been an artifact of mathematical smoothing in the data analysis. Even the ALMA observatory recalibrated its instruments, admitting potential errors in its earlier readings. The most damning blow came when follow-up observations failed to consistently replicate the phosphine spikes, leaving the original claim hanging by a thread. Yet the story isn't over. The original team stood by their work, insisting their methods were sound and calling for more advanced telescopes to settle the debate. Meanwhile, astrobiologists began brainstorming how life could survive in Venus clouds, perhaps as extremophile microbes encased in acid-resistant shells, floating in a perpetual aerial ocean. Others speculated about a life cycle where organisms might rise and fall with atmospheric currents, seeding chemical traces as they go. What makes the Venus phosphine saga so compelling isn't just the did we or didn't we of it all, it's how it exposed the razor's edge of discovery. Science isn't a straight line from hypothesis to truth. It's a messy, contentious dance of evidence and doubt. Venus, that broiling enigma next door, reminded us of something profound. The universe loves a good plot twist. And whether the phosphine was real or not, one thing's certain: we'll keep looking. Because sometimes the most electrifying discoveries aren't the answers we find, but the questions we can't shake. Deep in the heart of our galaxy, where stars crowd so thickly they blur into a golden haze, there's a glow that shouldn't exist, a persistent hum of gamma rays with no clear source. Astronomers call it the galactic center excess, and it's one of the most tantalizing misfires in modern astrophysics. Picture turning up to a packed concert, hearing a mysterious melody woven through the noise, but no matter how hard you search, you can't find the musician playing it. That's the frustration and the thrill of this unexplained energy signature, first spotted by NASA's Fermi Gamma Ray Space Telescope in 2009. At first glance, the excess seemed like cosmic static, just another quirk in the Milky Way's bustling core. But as researchers peeled back layers of known gamma-ray sources, pulsars, supernova remnants, even collisions of cosmic rays, the glow stubbornly remained. It wasn't just noise, it was a signal, and its peculiar properties set off alarm bells. The gamma rays clustered symmetrically around the galactic center, their energy profile peaking at around 2 gigaelectronvolts, a fingerprint that didn't match any known astrophysical process. It was as if someone had left a cosmic breadcrumb trail leading straight to the galaxy's darkest secret, dark matter. The dark matter hypothesis quickly took center stage. If these elusive particles exist, theorists reasoned, they might annihilate or decay when they collide, releasing bursts of gamma rays as a byproduct. The Milky Way's core, packed with dark matter, would naturally glow with this telltale radiation. Simulations showed certain dark matter candidates, like weakly interacting massive particles, or WIMP, could perfectly reproduce the excess's energy signature. Suddenly, what looked like an anomaly might be our first glimpse of the universe's hidden scaffolding. But science rarely gives easy answers. Skeptics pointed to more mundane explanations, like a population of millisecond pulsars too faint to resolve individually. These rapidly spinning neutron stars, relics of dead stars, emit gamma rays in steady beams. If thousands of them crowded the galactic center, their combined glow might mimic the excess. Supporting this, Fermi later detected similar gamma-ray patterns in other dense star clusters. Yet the pulsar theory has its own holes, like why we don't see the expected radio or X-ray counterparts. Then there's the wild card, cosmic rays slamming into dense gas clouds near the center. Under the right conditions, these collisions could produce gamma rays in the exact energy range observed. But modeling the complex interplay of gas, magnetic fields, and particle acceleration, is like predicting the path of a pinball in a storm. Small uncertainties cascade into huge gaps. What makes this debate so electrifying is how it exposes the limits of our tools. Fermi's resolution is like trying to read a street sign through frosted glass. We see the light, but the details blur. Upcoming telescopes like the Cherenkov Telescope Array promise sharper vision, potentially spotting individual pulsars or confirming dark matter's fingerprint. Until then, the excess remains a cosmic Rorschach test. What you see depends on what you believe, and that's the beauty of the mystery. Whether it's dark matter's whisper or a chorus of unseen stars, the galactic center excess is forcing us to rewrite the rules. Every flicker of gamma light is a one that might finally crack open the universe's best-kept secret. The Big Bang wasn't just an explosion, it was the ultimate alchemist's furnace, forging the universe's first elements in a white-hot frenzy. Within minutes, protons and neutrons fused into hydrogen, helium, and trace amounts of lithium, setting the stage for everything to come. But here's the cosmic irony. While hydrogen and helium match predictions almost perfectly, lithium falls short, dramatically short. According to the math, the universe should contain 3 times more lithium than we actually observe. This isn't just a rounding error, it's a glaring hole in our understanding of the universe's first moments, and it's called the cosmic lithium problem. So where did the lithium go? One possibility is that we're misreading the cosmic recipe. Big Bang nucleosynthesis models rely on precise nuclear reaction rates, tiny probabilities that determine how often particles collide and stick. If these rates are slightly off, the lithium yield could be wrong. Some theorists suggest overlooked quantum effects might alter how lithium-7, the isotope in question, forms or breaks apart in those early chaotic seconds. Imagine baking a cake where one ingredient secretly evaporates halfway through. You'd end up with a very different result than the recipe promised. Then there's the stellar sinkhole theory. Stars, especially ancient ones, might be devouring lithium over time. Surface convection in these aging suns could drag lithium down to hotter layers where nuclear reactions destroy it, like a cosmic recycling plant shredding evidence of its raw materials. Observations of some of the universe's oldest stars, like those in the Milky Way's halo, show lithium levels even lower than expected, hinting at this slow-motion destruction. But here's the catch: not all stars exhibit this behavior, and the overall deficit is too large for stellar processes alone to explain. The plot thickens with exotic physics. What if unknown particles like certain types of dark matter interacted with early nuclei, altering lithium production? Or perhaps the universe underwent a phase transition we haven't accounted for, briefly changing the rules of nuclear physics during those critical first minutes. Some models even propose that lithium gets trapped in hypothetical cosmic structures like quark nuggets or domain walls, hiding it from our telescopes. But the most tantalizing clue might lie in the stars themselves. In 2020, astronomers discovered a rare class of red giants with unusually high lithium levels, stars seemingly defying the norm by producing lithium as they age. If these stellar outliers hold the key to lithium creation, they might also hint at destruction mechanisms we've yet to unravel. It's like finding a single survivor at the scene of a crime, holding a clue that changes everything. What makes this puzzle so gripping isn't just the missing lithium, it's what it reveals about the fragility of our cosmic models. The Big Bang's predictions have been stunningly accurate for hydrogen and helium, but lithium's discrepancy is a stark reminder. Even our best theories are incomplete. Every telescope pointed at ancient stars, every particle accelerator probing nuclear reactions, brings us closer to solving the mystery. And when we do, we won't just find the lost lithium. We'll uncover a new chapter in the story of how the universe built itself one atom at a time. Somewhere out there in the vast cosmic map, there's a place so empty, so eerily cold, it might as well be a bruise on the skin of the universe itself. Astronomers call it the Eridanus supervoid, a staggering billion light-year-wide region where the cosmic microwave background, the afterglow of the Big Bang, dips to temperatures colder than anywhere else. This isn't just a random fluctuation. It's a cosmic anomaly so massive it defies our best models of how the universe should look. And if that weren't strange enough, some scientists think this void might be something far more mind-bending, evidence of a collision with another universe. Picture the cosmic microwave background as a baby picture of the universe, a snapshot of its fiery infancy frozen in time. Normally, it's speckled with tiny fluctuations, hot and cold spots no bigger than a few 100,000 light-years across, the seeds of galaxies and galaxy clusters. But the Eridanus supervoid is different. It's a cold spot 10 times larger than any statistical fluke should allow, stretching across such an incomprehensible distance that if you stood at one edge, even the most powerful telescopes couldn't see the other side. The odds of this happening by chance, less than 1 in a million. It's like rolling a die 1,000 times and getting the same number every single time. Something's clearly rigging the game. So what could carve out a void this enormous? One theory points to dark energy, that mysterious force accelerating the universe's expansion. If dark energy behaved oddly in this region, it might have pushed matter apart faster than elsewhere, leaving behind a titanic bubble of near-nothingness. But even that doesn't fully explain the cold spot's extreme temperature drop. That's where things get wild. Some cosmologists suggest this void isn't just empty space, it's a scar. A collision point where our universe might have bumped up against another bubble universe in the multiverse, draining energy from our cosmic background radiation like a phantom stealing heat. Think of it like pressing an ice cube against your skin. The spot where it touches grows cold, not because something's actively cooling it, but because energy's being siphoned away. If another universe brushed against ours in the distant past, its gravity could have tugged on ours just enough to leave this massive cold imprint in the CMB. It's an idea straight out of science fiction, except the math kinda checks out. Simulations show such collisions could produce voids and temperature anomalies eerily similar to what we see in Eridanus. Of course, not everyone's convinced. Skeptics argue the cold spot might just be a trick of perspective, an illusion created by overlapping smaller voids that happen to line up along our line of sight. Others propose exotic physics like primordial black holes or defects in spacetime structure left over from the Big Bang. But the multiverse explanation has one irresistible allure. If true, it would be our first tangible clue that other universes aren't just theoretical fantasies. They'd be real, detectable, and maybe close enough to leave marks. What makes the Eridanus supervoid so electrifying isn't just its size or its coldness, it's the sheer audacity of what it implies. This isn't just a puzzle for cosmologists to solve. It's a dare from the universe itself, pushing us to question whether we're alone in the cosmic ocean or just one bubble in an endless foam of realities. And until we crack its secrets, that cold spot will keep staring back at us, a silent challenge written in the oldest light there is. Saturn's North Pole is home to one of the most baffling weather phenomena in the solar system, a perfectly geometric hexagon large enough to swallow 4 Earths whole. This 6-sided jet stream, spinning like a cosmic top for decades, defies everything we know about fluid dynamics. Storms don't form hexagons, clouds don't organize into crisp, angular shapes. Yet there it is, a near-perfect polygon etched into Saturn's atmosphere, so precise it looks engineered. The hexagon was first spotted by NASA Voyager missions in the 1980s, dismissed at first as a trick of the light or a fleeting atmospheric quirk. But when Cassini arrived in 2004, the structure hadn't just persisted, it was immovable, anchored to Saturn's rotation like a celestial tattoo. Inside its 6,000-mile walls, winds scream at 320 kilometers per hour, yet the hexagon itself rotates just once every 10 hours and 39 minutes, syncing eerily with the planet's deep interior. It's as if someone drew a border in the sky and told the storm no further. Explaining this geometric freak of nature pushes physics to its limits. On Earth, turbulent systems like hurricanes and ocean currents spiral into curves, not angles. But in lab experiments, scientists have recreated faint echoes of the hexagon by spinning fluids at different speeds, creating shear forces that generate polygonal shapes. The key might lie in Saturn's layered atmosphere, where gases at varying altitudes shear past each other like sheets of ice on a pond, locking turbulence into rigid patterns. Think of it as a cosmic lathe carving chaos into order through sheer rotational might. Yet mysteries linger. Why 6 sides? Simulations can produce polygons with anywhere from 3 to 8 sides, but Saturn's hexagon is unnervingly consistent. Some theorists point to standing wave phenomena, where atmospheric oscillations reinforce specific geometries like sound waves shaping a vibrating plate. Others suggest the hexagon is a towering vertical structure rooted deep in Saturn's interior, with its shape governed by hidden planetary magnetic fields. The most haunting question isn't how, but why this storm alone, on this planet alone, defies nature's aversion to straight lines. Every close-up image from Cassini reveals new layers, smaller vortices dancing along the hexagon's edges, its color shifting with Saturn's seasons, even hints that its shape might slightly oscillate over time. It's a reminder that even in a universe ruled by chaos, there's room for the inexplicable, a storm that plays by its own rules, etching geometry into the sky of a gas giant. Look up at the night sky just before dawn or after twilight, and you might catch a faint, ethereal glow stretching upward from the horizon, a ghostly pyramid of light often mistaken for the first hint of sunrise. This is the zodiacal light, sunlight reflecting off countless dust particles scattered throughout the inner solar system. For centuries, astronomers assumed this dust was simply leftover debris from asteroids and comets drifting lazily around the sun. But when modern spacecraft began measuring the actual density of this interplanetary dust, they stumbled onto something baffling. There isn't nearly enough of it to explain the zodiacal light's brilliance. The numbers don't add up. This discrepancy isn't just a minor accounting error. It's a full-blown cosmic mystery. The dust we can detect from asteroid collisions and comet tails accounts for only about 10% of the material needed to produce the zodiacal light's glow. So where's the rest? One leading theory suggests we're missing an entire population of dust-producing objects, perhaps a faint, previously undetected reservoir of comets lurking in the solar system's inner reaches. These dark comets, nearly invisible to telescopes, might be constantly disintegrating as they approach the sun, shedding dust in their wake. Imagine a hidden conveyor belt of icy wanderers, silently crumbling and replenishing the zodiacal cloud over millennia. But the plot thickens. Some researchers argue the missing dust might not come from asteroids or comets at all. Instead, they point to Mars as an unlikely culprit. The red planet's thin atmosphere and frequent dust storms could be launching fine particles into space, where solar radiation pushes them into orbits that amplify their collective glow. It's a cosmic game of ping-pong, with Mars acting as the paddle, batting dust grains into the inner solar system. Supporting this idea, NASA Juno spacecraft detected a puzzling dust ring near Mars' orbit during its journey to Jupiter, a potential clue that the planet is leaking material into the void. Then there's the wild card, interstellar interlopers. Recent discoveries like Oumuamua and Borisov have shown that objects from other star systems routinely pass through our solar system. Could a steady rain of such visitors be contributing exotic dust to the mix? Even if each interstellar object sheds only a tiny amount of material, their cumulative effect over billions of years might help fill the gap. The implications go beyond just solving a light puzzle. If the zodiacal discrepancy stems from unseen comets or Martian dust, it could reshape our understanding of how small bodies evolve and distribute material in planetary systems. And if interstellar dust plays a role, that opens a window into the composition of other star systems, carried here on the backs of nomadic space rocks. What makes this cosmic bookkeeping era so fascinating isn't just the missing dust, it's what it reveals about our blind spots. Even in our own celestial backyard, the universe holds onto its secrets tightly, reminding us that sometimes the most ordinary-looking glow can hide the most extraordinary questions. The universe has a strange habit of creating something from nothing, especially when motion gets involved. Imagine you're floating peacefully in the vacuum of space, where empty space is supposed to be truly empty. Now picture accelerating rapidly, as if strapped to a rocket. According to quantum physics, suddenly that void wouldn't feel so empty anymore. You'd find yourself bathed in a warm glow of particles popping into existence, a phenomenon called the Unruh effect, where acceleration alone conjures matter from thin air. This mind-bending prediction comes straight from the marriage of quantum mechanics and Einstein's theory of relativity. Empty space isn't really empty. It's a seething quantum foam where virtual particles flicker in and out of existence too quickly to detect. But when you accelerate, your perception of reality shifts. What looks like a vacuum to a stationary observer becomes a thermal bath of real particles to the accelerating observer, like the cosmic equivalent of wind rushing past your face, except the wind is made of newly birthed matter. The faster you accelerate, the hotter this phantom glow becomes, with particles appearing at energies proportional to your motion. Here's where things get paradoxical. While the Unruh effect is mathematically sound, derived from the same equations that underpin Hawking radiation, it's never been directly observed. The temperatures required to detect these particles are absurdly extreme. For an astronaut accelerating at 1 gravity, the Unruh radiation would be a frosty 4 × 10⁻20 Kelvin, far too faint for any instrument to measure. To produce a noticeable glow, you'd need accelerations trillions of times stronger, the kind only found near black holes or in hypothetical particle accelerators wrapped around entire stars. Some physicists argue the effect might leave indirect fingerprints. High-energy particle collisions could momentarily replicate the conditions needed, leaving subtle statistical anomalies in experimental data. Others propose that rapidly vibrating mirrors or ultra-intense laser fields might tease out signatures of this acceleration-induced radiation in lab settings. But so far, the Unruh effect remains stubbornly elusive, a ghost in the quantum machinery. The deeper puzzle: if acceleration creates particles, why doesn't the cosmos constantly light up with them? Stars orbit galaxies. Galaxies hurtle through clusters. Motion is everywhere. Shouldn't the universe be awash in Unruh radiation? The answer lies in relativity's nuances. Only proper acceleration, the kind you'd feel as genuine g-forces, triggers the effect. Free-fall motion, like Earth orbiting the Sun, doesn't count. It's a cosmic loophole that keeps the vacuum quiet for most observers. What makes the Unruh effect so mesmerizing isn't just its defiance of classical intuition, it's what it reveals about reality's fluid nature. Particles aren't immutable things, they're stories told differently depending on how you move. And until we catch this quantum mirage in action, it stands as both a triumph of theory and a tantalizing challenge. Proof that sometimes the universe's boldest ideas are the hardest to spot. Deep in the cosmic microwave background, the oldest light in the universe, there's a cold spot so bizarre it defies easy explanation. Spanning nearly 2 billion light-years across the Eridanus constellation, this frigid anomaly is colder than its surroundings by about 70 microkelvin. At first glance, that might sound negligible, but in the ultra-precise world of cosmology, it's a screaming red flag. The odds of such a massive cold spot forming randomly: less than 1 in 50,000. So what's really going on here? The debate splits cosmologists into 2 passionate camps, one arguing for an impossibly vast void, the other whispering about something even stranger, a bruise left by a collision with another universe. Let's start with the supervoid theory. Most cosmic voids, bubbles of relatively empty space, measure a few 100 million light-years across. But the cold spot's proposed void would need to be 5 times larger than any ever observed, a staggering cosmic vacuum where galaxies are suspiciously scarce. The idea is that photons from the CMB lose energy as they traverse such a void, a process called the integrated Sachs-Wolfe effect. Think of it like rolling a marble uphill. As light climbs out of the void's gravitational well, it stretches to longer, cooler wavelengths. But here's the catch: recent galaxy surveys haven't found conclusive evidence of a void big enough to explain the temperature drop. Some studies even suggest the region isn't particularly underdense at all, leaving the cold spot's origin hanging in the air like an unsolved equation. That's where the multiverse theory comes in, turning the mystery into something straight out of cosmic science fiction. If our universe is just one bubble in an infinite multiverse foam, collisions between neighboring bubbles could leave imprints, cosmic bruises where the energy of impact bled into our reality. In this scenario, the cold spot might be the aftermath of such a collision, a place where another universe's gravity siphoned energy from ours during the Big Bang's fiery infancy. The math is speculative but compelling. Simulations show bubble collisions could produce cold spots with similar size and temperature profiles. It's like finding a fingerprint on a window pane, hinting at someone or something pressing against the glass from the other side. But skeptics aren't ready to rewrite cosmology textbooks just yet. Alternative explanations range from statistical flukes, though the odds are slim, to exotic physics like cosmic textures, hypothetical defects in space-time structure left over from the universe's violent birth. Others argue the cold spot might be an illusion caused by foreground dust or instrumental noise, though repeated observations with Planck and WMAP satellites have largely ruled out such mundane explanations. The truth might lie in the middle, perhaps a modest void amplified by unknown physics or a rare fluctuation that's pushing our models to their limits. What makes this debate so electrifying isn't just the scientific stakes, it's the philosophical implications. If the cold spot is proof of a multiverse, it would be the first tangible evidence that our universe isn't alone. On the other hand, if it's just a void, it forces us to confront how little we understand about the large-scale structure of reality. Every new telescope pointed at this enigmatic patch of sky. From next-generation CMB observatories to galaxy mapping surveys brings us closer to an answer. Until then, the cold spot remains cosmology's ultimate Rorschach test. A cosmic ink blot that reveals as much about our theories as it does about the universe's deepest secrets. And in that uncertainty lies the thrill, because the most tantalizing possibilities are always the ones just beyond our grasp. Dark energy was supposed to be the universe's silent architect, a subtle force stretching space-time at a steady, predictable pace. But what if it's not constant? What if, instead of gently accelerating the cosmos, dark energy grows stronger over time, morphing from a quiet current into a cosmic tsunami? This nightmare scenario has a name: the Big Rip, an apocalyptic endgame where the universe doesn't just fade to black. It's violently shredded apart, atom by atom, in a crescendo of phantom energy. Picture this: trillions of years from now, galaxies aren't just drifting apart, they're being yanked apart at speeds that defy physics. First, galaxy clusters tear free from one another, their gravitational bonds no match for dark energy's mounting strength. Then, individual galaxies unravel, stars ripped from their orbits like petals in a hurricane. But the horror doesn't stop there. As the phantom energy intensifies, planetary systems disintegrate. Earth, if it still exists, will be torn from the sun's grip, then cracked open like an egg as molecular bonds snap. In the final moments, even atoms themselves are ripped asunder, protons and electrons torn apart in a flash of energy. The universe doesn't just end, it's executed with surgical precision. What makes this scenario so unnerving is how it twists our understanding of cosmic fate. Traditional thermodynamics predicted a heat death, where the universe cools into a uniform graveyard of exhausted energy. The Big Rip, though, is heat death's deranged cousin, an ending where dark energy doesn't just empty the cosmos but actively dismembers it. And here's the kicker: we might already be seeing hints of this future. Some measurements suggest dark energy's density could be increasing, behaving less like Einstein's cosmological constant and more like a runaway freight train. The math behind the Big Rip hinges on a parameter called W, the equation of state of dark energy. If W is exactly -1, the universe expands steadily. But if it dips lower, say -1.5 or beyond, dark energy's grip tightens exponentially over time. It's the difference between a slowly rising tide and a flash flood. Current observations hover tantalizingly close to the critical threshold, leaving cosmologists glued to their telescopes, watching for any sign the universe has crossed the point of no return. Could we stop it? In a word, no. This isn't a disaster you can outrun or outthink. The Big Rip isn't just an event, it's a rewriting of physics itself, where the fabric of reality becomes the enemy. The only silver lining: if it happens, it won't be for billions of years, but as a reminder of the universe's capacity for chaos. It's unmatched, a finale where even the laws that hold existence together are just cancelled. And that's the chilling beauty of the phantom energy hypothesis. It forces us to confront the universe not as a static stage, but as a dynamic, unpredictable force, one that might still have a few catastrophic surprises up its sleeve. So the next time you gaze at the stars, remember, the cosmos doesn't just fade, sometimes it fights back. From vanishing stars to phantom galaxies, rogue black holes to cosmic cold spots, we've journeyed through 30 of the universe's most defiant puzzles, phenomena that laugh in the face of physics as we know it. Each of these cosmic anomalies is more than just a head-scratcher for scientists. They're revolutions waiting to happen, breadcrumbs leading us toward discoveries that could rewrite entire chapters of our textbooks. Think about it: every time space breaks its own rules, it's handing us a clue, a glimpse behind the curtain of reality. These mysteries aren't roadblocks, they're invitations. The Pioneer Anomaly made us question gravity's grip. Dark matter forced us to admit we're blind to 95% of the universe. The wow signal teased us with the possibility we're not alone. And the Big Rip, it's a stark reminder that the cosmos doesn't owe us a gentle ending. What binds them all together isn't just their defiance of expectations, it's the way they expose how much we still don't understand. And that's the magic, because science doesn't grow by confirming what we already know. It leaps forward when the universe throws us a curveball. So here's to the cosmic rule breakers, the anomalies that keep astronomers up at night and physicists rewriting equations at dawn. They're proof that the universe is stranger, wilder, and more brilliant than we've dared to imagine. And the best part, this is just the beginning. Every new telescope, every daring mission, every curious mind staring up at the stars brings us closer to cracking these enigmas wide open. If these cosmic puzzles lit up your sense of wonder, you're in the right place. Hit subscribe, because the universe is packed with even more mysteries waiting to blow your mind. Stay curious, keep looking up, and remember, the next great discovery might be hiding in the very next anomaly we uncover. The cosmos loves a good plot twist. Don't miss what comes next.